Hi everybody, and welcome to our session today on reacting flows. So we have 4 speakers for you today. I'm just going to very quickly introduce everybody, and then we're going to get stuck into our first presentation. So we have Dr. Balut Tekul from the Aalto University in Finland. We have Dr. Chen Huan from the RISE Research Institutes of Sweden. We have Dr. Henrik Rusch from Wiki GmbH, and we have Dr. Ashish Vashista from the Institute of Technology, Kerala. So again, apologies for any pronunciations that might have gone astray there. So we have 1 hour, 15 minutes per talk, 10 minutes of a talk, and approximately 5 minutes of questions. So again, most of us will be reasonably familiar with the platform at this stage. But again, if people have questions, please put them into the questions part of the platform, and then when we get to the question stage of the talk, I'll do my best to get to as much as we possibly can, and everything else might be dealt with in the discussion forum afterwards. Okay, so with that said, we're going to jump straight into the presentations. So I'm going to ask our first speaker, Dr. Tekul, to share his screen and to start his presentation, please.
Thank you, Dr. Donovan. Can you see my slides now in full screen, if you can confirm?
Yes, we can see those.
All right, perfect. So hello, everyone. Good afternoon. And today I'm briefly going to talk about our new novel open source reactive solver, Dlbform, which is a dynamic load balancing model with analytical Jacobian for fast combustion simulations in OpenFOAM. This is the outline. So basically, I will start with describing current issues with multiprocessor reacting CFD in OpenFOAM. I will then introduce Dlbform and we'll try to explain how it resolves these existing issues. Then I will provide some benchmarking and validation against the standard chemistry models in OpenFOAM, and then just a single summary slide for, as a recap, basically. So if we just briefly talk about reactive CFD in OpenFOAM, it usually is done in a way that we directly integrate the chemical kinetics using finite rate chemistry in a single computational cell for each CFD cell in the domain. And chemistry solves an independent substep during CFD iteration as a separate ODE problem using this method called operator splitting. And it's computationally very expensive. So for instance, you can see in this time profile that species transport and chemistry together takes up about 97% of this particular simulation. So it's basically the driving bottleneck in reactive CFD simulations. And in specific to OpenFOAM, there are a couple of major issues. The biggest issue is that the parallel simulations suffer from load imbalance due to nonlinear nature of steep chemistry ODE. So you can decompose your domain geometrically using, some automated decomposition algorithm, but chemistry is quite nonlinear when it comes to, computational cost. So you will always have some load imbalance due to this nonlinear nature of the chemistry problem. And to mitigate this issue, OpenFOAM has no built-in balancing feature. It's just, everything is handled in processor-based. And this leads to a huge performance bottleneck in parallel simulation. So for instance, in this figure, you can see that the processor with the red bar is basically holding everyone back. There are also some other issues regarding OD problem formulation when solving the chemistry problem. First of all, the Jacobian evaluation is quite expensive in OpenFOAM, even though OpenFOAM, starting from OpenFOAM version 9, is supposed to be using an analytical Jacobian formulation, but it's still quite expensive. The OD solver routines are not really designed for small non-diagonal dense matrices, because usually chemistry problem is a pretty dense non-diagonal stiff matrix, and the OD solvers that are built in OpenFOAM are not really designed to handle these type of matrices. Especially the operations such as LU decomposition and back substitution are really problematic. So this leads to serious performance degradation with increased OD tolerance. So when you tighten your tolerances to get better accuracy, the evaluation time of chemistry just skyrockets, as you can see in this figure. And overall, this just makes OpenFOAM just not ideal for reactive CFD at all. Dlbform stands for dynamic load balancing for chemistry using MPI routines. So what we do is we kind of, balance the chemistry problem on the fly using MPI. And there's also this zonal reference mapping model for further performance gain. I will talk about it in a minute. We also have optimized ODE routines to handle dense Jacobian matrices, which includes a fully analytical Jacobian and also some improved ODE solver routines to handle, dense matrices. I think there's a repetition over there. So this first part is load balancing and reference mapping, and the second part is ODE improvements. I broke this into two so I can, break them up and explain one by one. So first of all, load balancing and reference mapping. The dynamic load balancing is basically we create this problem structure within OpenFOAM for each computational cell, and we put all the information that we need to solve the chemistry problem. And during runtime, we transfer these cells or these problems between busy and idle processors using non-blocking MPI communications. So you can see that by doing that, we can turn this into this during runtime. And we did some benchmarks, and with this approach, with non-blocking MPI communications, we can basically obtain close to theoretical speed up for different process and cell counts. The reference mapping is a supporting method to further enhance the speed up process. So the idea is we just group the cells sharing similar thermochemical composition values together, and we solve the chemistry only once for one of these cells and just map it to others. And the criteria is defined based on mixture fraction and temperature. We group these cells based on these user-given criteria. So for instance, in this problem, the algorithm picks a reference solution, it solves it, and it maps the solution to all the other, similar thermochemical states instead of solving every single cell in the domain explicitly. So this gives us tremendous speed up when bundled together with load balancing. So when I go to all these solver improvements, I'm sorry for rushing. I just want to get things, completed in 10 minutes. So first of all, we did a complete overhaul of the Jacobian class, and we implemented an analytical Jacobian, and it significantly cuts down the Jacobian evaluation. And for this, we actually didn't reinvent the wheel. We just coupled this open source library PyJack, which generates, C subroutines for analytical Jacobian to OpenFOAM. And you can see in here that PyJack, especially with, high number of reaction, provides at least an order of magnitude speed up compared to finite differencing for calculating the Jacobian. And it significantly improves the chemistry solution performance. You can see that we can obtain basically one order of magnitude speed up for the same zero-dimensional problem that we use for benchmarking. But on top of that, we still have to figure out the ODE solver routines, because as I said, they're not designed for dense matrices, and the Jacobian, especially an analytical Jacobian, is a full matrix. So for that, we just use LAPACK routines. Again, no need to reinvent the wheel. We just link the LAPACK routines, LAPACK ODE solver routines for dense matrices to OpenFOAM and just take out the standard ones. And when we do that, we actually reach a point where the tight tolerances are really not that effective on the evaluation time. So it's pretty fast when we couple PyJack and LAPACK together, analytical Jacobian and the improved ODE kinetics together. So to benchmark this, we came up with two test cases. The first case is a simple 2D case, reacting shear layer. It's formed with an air ambient and a fuel strip in the middle, and just some Kelvin-Helmholtz instabilities, by imposing some initial conditions. As I said, there's a fuel shear layer with a hyperbolic 10H function and sinusoidal perturbation. We have cyclic boundary conditions all over. We have around 160,000 cells divided into 64 processors using Scotch decomposition. So now I'm going to show you this animation. So the left-hand side, left block is the standard, and each line you see in the figure is one processor. The middle is Dlbform, which is load balancing and reference mapping, and the right-hand side is basically everything bundled together, Dlbform, PyJack, and LAPACK. And you can see that standard is a pretty, pretty big imbalance issue. We mitigate it with Dlbform when we apply load balancing, and when we also improve the ODE kinetics, the load is pretty much non-existent. So I can show you that for these given ODE tolerances, when we use Dlbform together with PyJack, we obtain speed up about 21 to 22 compared to standard model. And for tighter tolerances, because at tighter tolerances, LAPACK basically doesn't add any computational cost to the problem, we reach about 109 to 110 or factor of speed up compared to standard. But this is just a 2D case with a couple of thousand cells, and we wanted to check this in a bigger case. So we did a 3D LES of ECN spray. This case is a pretty good benchmark case, large-scale benchmark case for 3D simulations for showing practical performance. It's about 23 million cells divided into 640 processors, so around 36,000 cells per core. And again, we just use Scotch decomposition because the algorithm doesn't care about the geometrical decomposition. It just cares about the busy processors and the idle processors. The problem with this case is it's not possible to run a full simulation using standard or using Dlbform. The standard, a full simulation in 1 millisecond in simulation time can only be run by the full might of Dlbform and PyJack. So for benchmarking, I just did a benchmark for 100 iterations at the same time for each case. So on the left-hand side, you can see the results that we get from Dlbform PyJack. You can see that processors are just beautifully, lined up together and around the mean value, which means that, the load balancing algorithm is doing its job. Of course, you can see that there's some fluctuation, but this is due to, network issues and hardware-related issues that's really out of control of the algorithm. And you can see that the speed up is now about 225 compared to standard, which is significant. And this basically enables large-scale reactive simulations in OpenFOAM. And here's some validation against experimental data. And in conclusion, to summarize everything in one slide, Dlbform is a novel chemistry model built for OpenFOAM that features dynamic load balancing and zonal reference mapping. It features a fully analytical Jacobian via PyJack, which is another open source software. It features OD solver improvements via LAPACK, which provides significant speed up for tight tolerances, especially. And we obtain speed up to 250 with respect to standard OpenFOAM chemistry solvers. We have two preprints describing the implementation. The first one is accepted and it's focusing on the dynamic load balancing part. You can find it on arXiv. And the second part is about the OD solver and Jacobian improvements, which is also on arXiv, but it's under review. And Dlbform is completely open source and it's public at Alto CFD on GitHub. I'm actually asking for anyone interested to check it out and reach out to us or just create an issue if you have any questions. So thank you.
Thank you very much. A very, very interesting talk. Now I'm conscious that we will maybe have a couple of questions. We only have 2 minutes here, so I'm going to jump straight in. We have a question from Dr. Roosh. Why did you keep OpenFOAM's ODE solvers and not an ODE library, which would also bring in LAPACK for the dense matrices?
Can you repeat the question?
Why did you keep OpenFOAM's ODE solvers and did not, I'm assuming it means did not use an ODE library, which would bring in LAPACK for the dense matrices?
Well, the thing is, we only needed to change 2 matrix operations within the OpenFOAM ODE class, which was LU decomposition and back substitution of the decomposed LU matrix. So it didn't really make sense to just rewrite everything. What we did is we removed the 2 functions that are existing in OpenFOAM and just replaced them with LAPACK functions. And this kind of also provides, easier maintenance. Because when there's an update to the standard OD class in OpenFOAM, I know that the only thing that's different in my class is, apart from some other minor improvements, is the LAPACK implementation function. So I can easily maintain the code, basically.
Perfect. Now we are out of time, so I'm going to ask 2 questions to see if we might keep a succinct answer, and then everything else we might ask to go into the discussion forum. So the first is the dynamic load balancing working in combination with adaptive mesh refinement? And again, Dr. Tegula, I might ask for a reasonably succinct response if you don't mind in the interest of time.
Yeah. Well, yes, there are a couple of open source adaptive mesh refinement algorithms, for instance, from TU Darmstadt on GitHub. With little to no effort, you can basically couple them and run them together. I've done so. Please email me for further discussion on that.
Brilliant. And last question, how does the performance vary as the number of reactions increases?
The tests that we had done was about mechanisms with 50 to 100 species and around 200 to 500 reactions, because, you know, in reality, that's how much you can afford for 3D LES, which is what we do. But the idea is once you start using larger and larger mechanisms, the network bandwidth will also increase, because you would be transferring bigger and bigger data, you know, because the species size increases. So the largest that we went was 100 species. We didn't see any significant change in performance, but, you know, I don't know what would happen for even larger mechanisms.
Fantastic, Dr. Tegul. Thank you very much on behalf of everyone. And for those people whose questions we don't get to, I might ask you to put them into the discussion forum, and Dr. Tegul will be actually able to respond by text from there directly. So we will have to move on to the next speaker, but thank you very much.
Thank you.
So our next speaker is Dr. Chen Yuan from the RISE Research Institute of Sweden, who's going to talk to us about modeling of vented cornstarch dust explosion using OpenFOAM. So Dr. Yuan, over to you.
Yeah, thank you. Yeah. So today I'm going to present this work about modeling of vented cornstarch dust explosion using OpenFOAM. Yeah, so this is work is based on the ongoing project between RISE and Chalmers, which we want to develop tools and models to improve the safety in the process industries, which deal with combustible dust. So this is the outline of the presentation. I will start with the background and then followed by the method and model and the implementation. Then is the results and discussion. Finally is the conclusions. And these are some images showing some destroyed chain conveyors for the pellets. And yeah, so because when the combustible dust is normally formed in many different industries, like process industries and medical industries and food industries, when they mix with the air and when there is a hot ignition source, it burns like a premixed flame. So this is some accidents showing that is a problem in the industry, and we want to try to understand and to model it. And the method that we are using is that we are trying to, based on the assumption that the dust burning process resembles that of a gas burning process, which means premixed combustion process. And we are using the concept of a combustion progress variable, and it has a physical meaning of yeah, the probability of finding the burned products. And this is the image showing that yeah, so the premixed flame, and you have yeah, unburned, which is C equals to 0, and burned C equals to 1, and everything between the unburned and burned is between 0 and 1. It's within the flame brush. And we have implemented this model, and basically this solver is based on the already existing solver Dlbform. And here it's a balance equation for the regress variable B, which is 1 minus C. And you will see that, yeah, different terms is shown here. And yeah, the first is the transient, and the second is the gradient term, and third is the diffusion term, makes sure that the flame thickness is growing. And the fourth is the flame propagating term, where you have a UT, is the turbulent burning velocity, and there are some expression to it. And finally is the ignition source term. And we also made some changes in the temperature calculation in the thermodynamic libraries, where we disagree with some of the default implementations. And yeah, it's very important that if I implement a new model and I have to test that my implementation was the minimum amount of bugs as possible. So then I compare the model results with some benchmark analytical solutions. And for example, here is the flame speed versus time for the calculation. It's the dashed line, and the analytical solution is the solid line. And we see that they agree very well and make sure that there is minimum amount of bugs in the code that we are satisfied at the moment. And then we start doing some large scale simulations, and we are very lucky that we get some experiments with from RAMBI, where they made this experiment of in this 11.5 cubic meter vessel, where they have 2 small containers with pressurized cornstarch dust, and the dust is injected inside the vessel, and then the dust air mixture is ignited in the middle of the vessel with a pyrotechnical igniter, and then they measure the pressure development inside the vessel, and it's here it's this opening is closed with a very thin aluminum foil, and this will be activated when the overpressure is above 0.1 bar, and the purpose is to protect the increasement in the overpressure in the equipment, to protect the equipment. And on the right hand side is the simulation domain, and where this is the vessel, and also to simulate the venting process, the external domain is also included. And what I did is that I created the first mesh using, take the CAD geometry and made it using this free CAD program, and made it STL file and import it into the OpenFOAM, and made the mesh using the Snappy Hex mesh with finer mesh in the middle to resolve the ignition and initial flame propagating process. And then when the pressure inside the vessel becomes larger than the activating value, and then the result is the simulation is stopped, and the result is saved and mapped to a new mesh with a bigger domain, and to continue the simulation for the venting process. And here is some comparison with the experiments. And here is the, you will see that the y-axis is the overpressure and the x is the time. And you will see that the symbols are experiments and the line is the simulations. And you will see first the spike is due to the rupture of the opening and at the activation pressure of 0.1 bar. And we get quite reasonable agreement in the beginning. And then we continue the simulation with the venting process, and in order to better simulate this process, and we have to incorporate some flame acceleration mechanisms. And this is a typical dust flame. It's very wrinkled, and many literatures they say that this hydrodynamic instabilities, Kelvin-Helmholtz or related, are the reasons for those instabilities and flame accelerations. And we include that by including some statistics from the gas flames, and increase the turbulent burning velocity with a factor power square root of power of time in the model. And here are some results that we are using this round shape venting panel, and that the simulation is not going well in the beginning, and during the venting it's lower than the experiments. This is the original version of the model, but then we have improved it and added this acceleration sub-mechanisms, and which is makes the results much better compared to the previous version. This is the gray color, this simulation tool. And then, also it's interesting to study the venting shapes, because here is a square shape, and so here are some results. And if we don't include the acceleration mechanism it's not. Here it's okay, but if we include the flame acceleration mechanism, it's much higher than experiments. And what we are thinking that this might be due to the incapability of predicting the turbulence using the Reynolds averaged approach, which is used in this work. And here are some colorful images showing that, yeah, at different times and different flame development. And then there are some conclusions that we have implemented a dust exposure model, which is based on the premix turbulent combustion model, and the model and code were verified, and the simulation results are compared to the large scale experiments, but we still have challenges for different vent panel shapes, and this should be improved using more advanced turbulence approaches, like maybe large eddy simulations. Yeah, so this is the acknowledgements. Yeah, thank you also for the listening. So any questions?
Thank you very much, Dr. Duan. So just, I suppose, to the audience, if you have any questions, please put them into the chat and I can read them out and pass them on to our speaker. So just in terms of, to kick things off, you were saying that your experiments were primarily large scale. How did you find say, the influence on, say, model accuracy and obviously simulation time in terms of actually having to model such a large scale system?
Sorry, can you repeat your question?
You were saying your experimental validation was primarily captured on large scale equipment. Did you find there was any kind of impact due to the scale on the simulation versus experimental accuracy that you were seeing?
Actually, it was this is the second stage of the project. The previous stage we did simulations on a smaller scale, which is around 23 liter small fan stern vessel, and that we got a reasonable agreement with the experiment, and that is also very well defined lab conditions, and that's why we first verify our code and model they are correctly implemented, and then we validate with some lab condition fundamental experiments, and then we move to a large scale industrial applications. That's how we do that.
Fantastic, thank you very much. So we have a question: is there any dependence on the nature of the ignition source term?
Is there any dependence on the nature of ignition source term? Yeah. So because as I show in the slide, that the ignition source term is just working in a very small region inside the domain, and we did we did actually the sensitivity studies on the ignition kernel size and the ignition strength and the ignition duration, and it impacts in the beginning of the combustion process, but the later when we switch off the ignition model, then it does not have very little impact on the process.
Fantastic. Okay, Dr. Duan, thank you very much for your talk today. Really interesting, and appreciate your time. Thank you very much.
Thank you.
Okay, so then moving on to our next speaker, it's Dr. Henrik Rusch, who's going to talk about lowering the obstacles of for SMEs to adopt multiphysics biomass furnace simulations by providing a cloud-based solution. Dr. Rusch, over to you.
Thank you very much for the kind introduction. So let's jump in. So this is a collaboration work. My name is Henrik Rusch. I'm working for Wiki GmbH. And this has been a project within the cloud effecturing framework, which I will explain a little bit further in the talk, of the University of Luxembourg, Professor Peters and his group, and also the Anna Stener company who provided the biomass furnace problem. So as an introduction, biomass, and you can think of wood chips for the moment, is a combustion that is widely used in generating electric power and thermal energy, especially in wood-rich countries such as Lithuania and Finland and so on. It's renewable, and potentially it's a carbon neutral energy source. The combustion process is fairly complicated and requires advanced techniques to minimize harmful gas emissions. And if you are familiar with coal combustion, which is already quite complicated, the problem with the coal combustion you have is that the coal can vary quite a lot, but there you can actually control what you are burning. With biomass, you have much more variability in the feed that you have. So people try to burn almost anything like wood waste, straw, bark, olive pits, nutshells, and so on and so on. And you can imagine that the kinetics and the release of water, that they will burn very, very differently. And it's not just because of the chemical composition, they have different ash melting temperatures, humidity is different, and it causes all kinds of problems in the furnaces. One thing to note, many of the manufacturers of biomass furnaces are small to medium-sized enterprises. So it's not something that the huge companies, say Siemens, if you think of the energy producing market, have widely adopted. Unlike, for example, in wind energy, where you have a few very big players.
Dr. Hendrik, you are not sharing the screen.
Okay. Thank you very much for letting me know. That is my old problem. Here we go. This is better, yeah?
Yeah, that's perfect.
Good. Okay, so this is the slide that I have been not showing. Okay, so let's move on quickly. So the combustion process in a biomass furnace, it's basically shown here on the side picture. And what you see here is the biomass coming in, and it is moved through the furnace on a grate, on a forward-acting grate. And the wood chips, if you think of that, or the biomass, it's going through different processes. They will be dried, there is pyrolysis, there is some char burning, and the primary air release is actually in the air phase. So this should be efficiency and performance you would like to study in a numerical model. But this is rather complicated, and you can imagine that an Eulerian-based model will not be good enough. So in order to capture the physics on the wood chips, so what you would do here is to couple that with the DEM software. And we use XDEM, which is developed at the University of Luxembourg, which is a DEM code, but the X stands for extended physics on the particles, such as drying and combustion and release of chemicals. So they have very complicated models for the particles themselves. And also they have models for the biomass particles. We couple that to OpenFOAM for the Eulerian phase. So that solves the gas phase and the reactions within the gas phase. And the CFD coupling, it needs to capture the physics and offers quite unprecedented insights into the physics of biomass combustion. Obviously, this is coupled in a two-way manner, feeding data forward and backwards. This is rather complicated. So as you can imagine, we need to go through a process of generating the furnace. Here are some furnaces here and the furnace down here. This is the one that was under the investigation in the cloudy factoring project. This is not terribly complicated geometry, but it still has a few degrees of freedom. So this mesh needs to be generated, the case needs to be set up. You can see a number of air inlets here on the side. In addition, you also need to do all the initialization for the particle bed. You need to generate an initial particle bed that can then be fed and transported through the grate. And also the DEM has to be set up, and there is complications with the fuel. As you can imagine, there is a number of properties you need for the fuel and very little data. There is usually an ultimate analysis for the fuel, and that we use that to set up the fuel properties for the simulation. So if you think of that, putting this into the hands of an SME, this is quite a scary thought, I would say. And this is where the cloudy factoring project comes in. So the cloudy factoring project is an EU initiative to lower the entry barrier for SMEs to pick up such complicated ICT solutions. Not only CFD or DEM, but also data analysis and all sorts of other things. And empowering them to make use of such technology. So it brings, if you think of it as a table, it puts up a marketplace for the community, like research organizations, consultants like Wiki, to bring together different solutions and make them accessible through a cloud-based, web-based interface and marketplace. So these services in a cloudy factoring solution will be on a pay-per-use subscription business model with some billing process. But then you can also buy support, for example, or training through the marketplace. So it's a bit more overarching than a cloud solution itself. So we were at the beginning of the project, we were wondering how much data do you actually require? And basically what we come up with is that you need about a few hundred numbers to specify the minimum input for such a furnace. And some of it is geometry, some of it is mass flows and species and things like that. And the initial plan was to develop a web interface, but that was out of the question given the time in the project. So what we came up with as an alternative was to prepare an input file for the solution process. And we used a spreadsheet for that. And that can be nicely structured with sheets. And you can also add lines and rows, and you can also give some structure to it and also some online checking. So this is prepared by the user offline on his Windows machine. Then it's sent to the cloudy factoring web portal. The HPC analysis is done, and what he gets back is a pre-generated report from the web portal. As a snapshot, you see on the left-hand side a few sheets where the numbers are put in, and what you get as one of the input, one of the results or intermediate results is a ready-to-run mesh automatically generated from these inputs. The workflow is quite complicated, so every box is a software that is run, and the wavy boxes are files being exchanged. You get a picture of what is actually required. So it's quite a lot running behind the scenes. So on the front end, you have a submission sheet This looks a bit different in the cloud factoring platform. The code is run, you get the progress report, nothing too spectacular. And in the end, you get a download link with the report, and the report will contain the numbers and some graphs and pictures that help you to understand what is going on in your biomass furnace. So that was rather dry in terms of CFD, and so I brought some eye candy for you. What you see here is a simulation, a video of a running furnace. You can spot the grate transporting particles down the grate. What the color is the liquid water in the particles, and the color in the air is the gas temperature. Okay, so what we have here is a cloud-based workflow for a coupled DEM CFD simulation of a biomass furnace. It has been implemented and tested, and also validated against some results done in the project. We use a spreadsheet, which is new to provide input for a rather complicated setup, which is a viable low-cost alternative of implementing a problem-specific user interface for this kind of simulation. This application has been integrated into the cloud factoring marketplace as a part of the project, and the spreadsheet to report concept and the underlying workflows are obviously much more versatile and can be applied to other applications with and without the cloud, obviously. So it can be also used to automate simulations. So thank you very much for listening, and I'm open to questions.
Thank you very much, Dr. Bush. Very interesting. So we'll get stuck straight into the first question in the interest of time. So how is the coupling for CFD EEM done? Using PREC ICE?
No, in this case, actually, it's not. It's a native interface between Foam Extend and DEM and XDEM. I know that the guys in Luxembourg are looking into Precise, and there is also a version running, but we are not using it for this application.
Fantastic. Thank you very much. Do you have a plan to develop it for applications other than biomass furnace?
Yeah, sure. If there is an interest and somebody wants to has a vertical application that he thinks this would help, sure, yeah, then we would push it to the next problem. I think it's not the idea of what we are doing is not really combustion or even biomass combustion related. It's more a way of, I think it can be used also for day-to-day production runs. And it's also good, having the Excel sheets is good because you are everything that goes into the simulation is documented.
Thank you very much. And then in the event of runtime errors not resulting from input file issues, does the system offer debugging assistance for SMEs?
Yeah, that's a big issue. We've didn't quite get that far. I mean, if the workflow fails, it fails. But what we've started to do, well, the checking goes into different stages. We put a lot of input checks into the spreadsheet itself, because you can do a lot of checks. Like, okay, is the inlet inside or outside of the bounding box of your furnace, for example? Yeah, and that can be checked without having to go to any resources. We also do some checking on the inputs, mainly on XDEM, because as you know, OpenFOAM is not that good at a priori checking. And that would be sort of reported, but you would get that report only after you have been queuing for the HPZ resource. That can be factored out, but we haven't gone quite that far because you need a few steps, and some of them take a few minutes. So that's why we split it this way. So yes, there is checking on various scales, and as any checking, it can be so much better.
Fantastic. Now, very last question, and I will have to ask you for a reasonably concise answer for this if you don't mind. Any comment about HPC scaling on such a cloud-based system?
We used, so Cloudifactoring gives access to HPC systems, so true HPC systems at IT for Innovation in the Czech Republic. So actually we used true HPC. And on the other hand, it is not such a huge simulation. So you could actually get away with a fat node on Amazon. But we didn't quite know at the beginning of the project how bad it's going to be. So that's why we went through HPC.
Dr. Rusch, thank you very much. Very interesting talk, and I wish you all the best with it. Thank you. To our final presentation of the session, so Dr. Bashista, and this is looking at numerical simulation of hydrogen injected in high-speed crossflow. So thank you very much, and over to you.
Thank you, Dr. Felix, for introduction. So I'll just share my screen and let me know if you can see the screen now.
Yes, we can see your screen. Thank you.
Okay. Thank you very much. So today I'll be talking about numerical simulation of hydrogen injection in high-speed crossflow. So this is the work I have done by using one of the solvers which was developed by TU Munich in 2014, if I remember right, and with my own interest or academic interest for hydrogen injection in high-speed propulsion systems. So basically, my background is aerospace engineering, and I have previously worked in hypersonics and with shockwaves a lot. So that's where I find the interest here, and that's the reason I actually kind of presenting this work here. So in high-speed transport, basically, if some of you might already heard about, like there are different combustion systems like a scramjet, supersonic combustion ramjet. There is a detonation-based system. I will come back to you again, like why the detonation-based system, which might be seen as a future propulsion systems for high-speed aircraft. Some are like oblique detonation wave engine, which is somewhat similar to a scramjet and which actually generate a detonation wave near the combustion zone. Then there is a pulse detonation engine, and there is also a rotary detonation engine. So most of these concepts, there are a lot of research working on in different parts of the world, and they have been under development for past couple of decades. A lot of people are using premix systems for these combustion system development. And now there is slowly there will be interest in non-premix side of those combustion systems because of battery control and all. So here, basically, let's come back to the basics of deflagration and detonation, why detonation-based systems are important here. So basically, there is a difference between deflagration and detonation. So usually, normal kind of fire that you see, or kind of a combustion you see in gas turbine combustors, they are mainly deflagration combustion, like a low-speed combustion. Then there is another kind of combustion which is called detonation combustion. You can actually find a kind of a wave between the product and reactant, and these are different properties. You can see the pressure change across the detonation wave will be tremendously higher than the deflagration wave. Of course, the moving deflagration wave, deflagration combustion flame may have a pressure rise, and also there is a temperature variation between those two flames can be slightly similar. So basically, subsonic combustion is called deflagration, and supersonic combustion, where you have a flame and shock wave travel together, is called detonation. And these are the characteristics of detonation wave, where you have a cellular structure. And in principle, on the cycle side, if you can see, there is the Brayton cycle and there is a Humphrey cycle, which is a constant. Brayton cycle is a constant pressure cycle, and then Humphrey cycle is constant volume cycle, and then you have a detonation cycle, which is called Pickup cycle. And the efficiency of those cycles, you can see the detonation cycle has a higher efficiency among all those three. So the motivation of and the objectives of this study was because we can see if we inject the hydrogen in a kind of a high-speed cross flow in any of those kind of systems, hydrogen have very low ignition energy requirements. So it can actually, because of the shock wave, it can burn itself and it can generate the flame. Here, the interest was to understand the fuel jet ignition and hypersonic cross flow for hydrogen injection, so that this kind of understanding can be later on led to use of non-premix kind of detonation-based systems. So here hydrogen has chosen because of its properties, and basically, as I said, because of the shock wave, the hydrogen can burn itself, self-ignite itself, and then it can also depends on the availability of fuel, air mixture, and other parameters. It can turn into detonation wave. So there is another concept of inclined wedge, which can generate an oblique detonation wave. So which actually initially it will be a shock wave, then it will ignite the hydrogen air mixture, and then it can turn into detonation wave for a premixed incoming flow. So the objectives of this study is to study the effect of sonic and supersonic hydrogen injection hypersonic cross flow for its stability and of shock wave and flame, and effectiveness of understand the effectiveness of the wedge inclination to obtain detonation condition from non-premix conditions. So these are, as I said, I have used a Dlbform solver, which was developed by TU Munich, and it is basically unsteady compressible Navier-Stokes solver. And here the deflagration and detonations are modeled as a source term in transport equation. And so deflagration is modeled with Weller combustion model, and detonation is modeled by auto-ignition delay time. And here, basically, I have done the two-dimensional simulations for hypersonic flow, and there is another set of case where I have introduced the wedge to introduce so that if it can generate a detonation wave or not. So before that, first I have simulated the premix system here to show if this solver can generate a detonation wave in oblique detonation front kind of thing. So you can see there is a detonation wave generation, and where actually you have small kind of shock cells which we can visualize here, and there is a pressure increase up to 25 times, and the temperature increase. Both are happening in a very small zone here, and there is a OH distribution on that flame. So for jet and cross flow, basically I have introduced sonic and supersonic cross flow of hydrogen, and there are different parameters. So I'll be just rushing through. So there are actually 3 cases which I have simulated: 10 and 50 and 125 grams per second in a hypersonic flow of Mach 7, and with the pressure and temperature conditions as given here. So basically, if in a straight domain, it's an unconfined domain. You have a far field here, you have an outlet here, it's oncoming, and there is a wall and a slip wall basically, and I have injected the hydrogen here. So these are 3 different cases for sonic jet injection. Like you can see, there is a shock wave and there is a flame which are separated, and there is a non-burned hydrogen which is left because of the high-speed flow, of course, and the available oxygen is consumed in this zone, and then there is no oxygen left. So that's the reason you have a unburned hydrogen left in this zone here. So this is again a supersonic injection of hydrogen for these 3 same mass flow rates, and here the comparison of these. So this is basically a flame for one mass flow rate, and this is a shock wave. And you can see they are separated. There is no detonation inside for a non-confined region because the reason is non-confined. We have a free stream flow, and just by hydrogen injection we cannot obtain a detonation front here. So the point here is, if we have a better fuel air mixing or a proper injection strategies, we can might obtain a detonation there. So there is another case where I introduced wedge, which again shows there is a combustion, there is a flame, but it actually kind of a shift to along with the wedge, but there is no detonation inside. So then in another attempt, I have introduced a confined domain where I have used the dual injection of hydrogen, which actually turn into which initiates the detonation, if you can see in the non-premix zone, but it will actually travel forward again as a blast wave because of the no hydrogen availability in the incoming flow. So overall, this study shows that the direct hydrogen injection in hypersonic free stream can lead to self-ignition behind the bow shock, and the penetration of supersonic injection is better for same mass flow rate than the sonic injection. And there is no detonation in direct hydrogen injection case. So the unconfined wedge stabilizes the flame, but there is no proper pressure gain combustion. So the dual injection in confined zone with wedge shows initiation of detonation wave, which can turn into blast wave and propagate upstream. And so the future work will be to explore the injection strategies for better mixing of fuel air mixture and detonation initiation in non-premix combustion system, and also to develop open source Dlbform solver for multi-fuel detonation combustion. There are actually few labs which has developed Dlbform for further use of multiple fuels, but it's not available in open source. So I'll be kind of looking for the future work into that direction. Thank you.
Thank you very much. Really interesting talk.
So it was a short time, but I tried to.
you did well. You did well. You kept it in there. So well done. So I'll again open up to the room if anybody has any questions. So before we start into the questions, just a question. You were saying your last point. One of the kind of future ambitions is to develop this open source solver. How much, I suppose, from what you've done so far, how close to that kind of position do you think the work that you've just presented would it be?
So right now what I have done is I have used already developed solver, so I have not introduced any development there. So I was just trying to show like if this kind of solver which was developed for straight tube detonation combustion can be used for different detonation domains. So of course, to introduce any other fuel, I might need to go into the source code and modify some of the things. So which is a future plan, and depends, like it might take 1 or 2 PhD students to develop in that sense.
Absolutely, nice bit of work to go in there. That's perfect. So we're just still waiting for any kind of questions to come through. I know it's kind of towards the end of the day. So again, we'll maybe give it a moment or two, just see if anyone else is going to come in the last minute. And so I suppose, like from your perspective, just in that kind of study, like, I mean, on some of the results that you were kind of presenting, one of the things I maybe was kind of wondering as you're going through in terms of the expectation of result versus what you actually got from those simulations in the end. But would you maybe want to comment on that?
Yeah, so the expectation was like if we have a premixed mixture and we have a wedge there, and we can actually, it's an experimentally established fact, like you can have a detonation wave in front of that wedge. So that's the reason actually this solver is good in the sense like this can give you a quick result. You can actually analyze a lot of different combinations in very short time. For oblique detonation, there is a very small range in which actually you can get a stabilized detonation wave in front of a wedge. So in that sense, actually, till now, I would say like the expectation was to get a proper mixing and proper detonation wave in case of a non-premix sense, but it might require further work to actually optimize the proper distance for getting the, like, where you need to particularly inject your hydrogen so that you can actually achieve detonation in front of the wedge.
Fantastic.
So it will take surely like a lot of simulations, but it might take some time. Yeah.
Fantastic. And is this continuing work? Is this something that
we'll see
again in the future?
Yeah, this is kind of a continuing work. So like it's going on for a couple of months. Yeah.
Fantastic. Well, that pretty much wraps us up. We're down to the last 20 seconds of our session. So thank you very much for your talk. That was really, really interesting. And again, wish you the very best with that going forward. So again, just the final bit from me is to thank all 4 of our speakers. I think you all presented something really, really interesting and valuable for our audience. And again, loads of different angles. So thank you very much to everybody and to everyone who was in the session with us here today. So I'm going to close it out at that. Thank you very much to everyone, and we're looking forward to seeing the next iterations of all of your work.